Welcome, curious learners, to another deep dive. Today, we're embarking on an extraordinary journey to a truly unique corner of the world, a place often whispered about as the land of the thunder dragon, the fascinating kingdom of Bhutan.
Fascinating indeed.
You've shared with us a rich collection of sources, notably a comprehensive project report on its mineral resources and a detailed geological account of the Bhutan Himalaya. Our mission today is clear: to unpack the geological wonders of this, well, somewhat secretive kingdom, peeling back layers of rock and time, and understand how its ancient, deep history fundamentally shapes its future, particularly its approach to development and its hidden mineral potential.
Indeed, it's a profound intersection of culture, environment, and of course, geology. Bhutan's very landscape, from its soaring peaks to its lush valleys, tells a dramatic story of immense geological forces at play. Understanding that deep story, reading the Earth's chronicle, is absolutely key to appreciating Bhutan's unique approach to progress and prosperity. We'll be connecting the dots between its majestic mountains, its foundational philosophy of gross national happiness, and the surprising and often challenging mineral potential hidden within its ancient, contorted rocks. It's a place where the Earth's raw power and human values are in a constant, fascinating dialogue.
Absolutely. Let's start right there with the landscape. So let's begin by just getting a mental picture of this incredible geography. Bhutan is nestled snugly at the southeastern foot of the mighty Himalayan range. But it's not just any mountainous country. It boasts a dramatic terrain that plunges from lowlands at a mere 100 meters altitude in the south, right up to towering peaks of 7,550 meters in the north.
Wow.
That's a staggering difference in elevation, over 7,400 meters across a relatively small country. It makes it one of the most vertically diverse nations on Earth. How does that extreme topography immediately hint at its geological origins?
But what's truly fascinating here is how that extreme, almost dizzying topography directly reflects its violent geological origins. This isn't just steep land, it's a direct outcome of the immense ongoing forces.
The plate collision.
Exactly. The Indian and Eurasian plates colliding, crushing, and uplifting the crust to create the Himalayas. Now, despite the fact that a 1991 United Nations report actually highlighted various mineral resources within this geologically rich landscape.
Right, I remember reading that.
Comprehensive information about Bhutan's geology and mineral wealth has remained surprisingly scarce until relatively recently, and there are very good reasons for that. The primary reasons cited in our sources are the insufficient and largely unsystematic geological surveys that have been undertaken historically.
Makes sense.
These efforts were compounded, of course, by the intensely challenging steep terrain itself, which makes physical access and systematic mapping incredibly difficult.
Just getting around must be a huge challenge.
Immense. Add to that underdeveloped infrastructure in many remote areas, and you have a land rich in potential, but guarded by its own natural defenses, and the sheer logistical complexities of exploring such rugged territory. It's like having a treasure map, but no clear path to the X.
That's a perfect analogy. So we have this incredible, rugged, geologically active landscape. But what makes Bhutan truly stand out is its guiding principle: gross national happiness, or GNH. This isn't just a catchy phrase or a national slogan. It's the nation's core development philosophy, promulgated by His Majesty Jigme Singye Wangchuck back in the early 1970s, and later enshrined in the 2008 Constitution. It emphasizes balancing material and non-material values for holistic and sustainable development. How, then, does this unique and deeply ingrained approach influence something as resource-intensive as mineral development, which often involves significant environmental impact?
Yeah, this brings us to a crucial point, and it's a question that Bhutan grapples with uniquely.
Yeah.
How does a nation so profoundly committed to deep environmental conservation, explicitly stating it will maintain at least 60% forest cover for all time? How does it approach something like resource extraction, which by its very nature can be disruptive?
That's the central tension, isn't it?
It really is. The government has actually enacted strict laws to ensure this commitment, and currently, an impressive 70.47% of its total land area is under forest cover.
Wow, over 70%.
Yes. And even more remarkably, over 51% of its land falls under a vast network of protected areas, 10 national parks and wildlife sanctuaries, all interconnected by biological corridors.
That's an extraordinary commitment.
It truly is. Yet despite this profound commitment to conservation, the royal government of Bhutan has pragmatically listed mining as one of its 5 jewels for economic diversification in its 12th five-year plan.
5 jewels. Interesting. What are the others?
The others are hydropower, cottage and small industries, tourism, and agriculture. So mining is recognized alongside these pillars. This designation acknowledges mining's recognized economic role and its potential for growth. For instance, in 2017, the mining and quarrying sector contributed 4.86% to the nation's GDP.
Okay, so not insignificant.
Not at all. And it even saw a significant growth of 37.56% in 2018, with gypsum and marble mines being the highest contributors. So there's clear economic intent. However, and this is the crucial part, the law explicitly requires strong overarching environmental consideration.
Right.
This means that any development, from the very earliest exploration stages through operation and even mine closure, must inherently prioritize environmental conservation and comply with strict mitigation measures. It often requires comprehensive environmental impact assessments, EIAs, even for relatively small-scale exploration activities in certain areas.
So it's baked into the process from the start.
Exactly. It's not just a balance, it's a constant negotiation, a tightrope walk, where the goal is coexistence between environmental protection and mining industries. And this is acceptable only in limited areas with high mineral resource potential where impacts can be minimized and managed. It's a pioneering approach to development, really, asking how a nation can prosper without sacrificing the very well-being of its people and its planet.
A fascinating challenge. Let's dive deeper into the rocks themselves. Geologists are truly like detectives, aren't they? Piecing together the Earth's deep past from the clues left in the rocks.
Absolutely.
Given the extreme challenges you mentioned, the rugged terrain, the limited early access, when did the first significant attempts to map Bhutan's incredibly complex geological history actually begin? And what did they reveal?
You're absolutely right. It's a painstaking process, almost like assembling a massive ancient jigsaw puzzle. Early mapping efforts were absolutely critical in laying the groundwork for our understanding of Bhutan's geology. One of the pioneering figures was Augusto Ganser, who in 1983 published one of the first geological maps that filled in the previously uncharted northern mountain areas. A monumental effort given the conditions back then.
I can only imagine.
That was followed by the UNESCO-compiled geological map in 1991. What's remarkable is that the broad geological distribution established in these early maps, particularly for eastern and central Bhutan, has largely remained consistent. They form the basis of our current understanding.
So those early efforts were pretty accurate then.
Largely, yes, for the major structures. The most recent significant compilation was by Long and his colleagues in 2011, which integrated existing published maps with valuable new structural data, further refining our understanding of the historical geology of the region. These cumulative efforts are incredibly important because, simply put, without a clear, detailed geological map, any systematic mineral exploration is nearly impossible. It's the foundational blueprint.
Got it. So with these foundational maps in hand, what story do they actually tell us about the ages and types of rocks that make up Bhutan? I understand we're looking at a vast span of geological time. It's like tracing Earth history through Bhutan's very backbone.
Absolutely. It's a truly vast geological timeline etched into the landscape. The Himalayan mountain chain, and by extension Bhutan, is fundamentally a massive fold and thrust belt.
Okay, unpack that term for us a bit, fold and thrust.
Imagine two colossal tectonic plates, the Indian and Eurasian, slowly but relentlessly pushing against each other, like two giant continents in a cosmic sumo wrestling match.
Okay, slow motion collision.
Exactly. As they collide, the Earth's crust is squeezed, folded like paper, and then huge slices of rock are shoved one over the other along massive faults. These are the thrusts, creating towering mountain ranges. That's a fold and thrust belt. Now, this region in Bhutan is structurally divided into four main tectonic zones, each separated by these immense thrust faults that extend east-west along the entire Himalayan arc. And as we move from south to north, these distinct geological ages and formations tell a chronological story of this collision.
Ah, okay, so it's layered history, south to north.
Precisely. First, to the very south, we have the sub-Himalaya. This zone is characterized by Miocene to Pleistocene molassic sediments.
Molassic.
Think of the rising Himalayas acting like giant rock factories, grinding down ancient rocks and washing the eroded material like sand, gravel, and mud into vast basins. These molassic sediments, like sandstone, are essentially the geological debris, the rubble, of the rising mountain range. They represent the most recent geological chapter.
Right, the stuff eroded off the top.
Exactly. Moving north from there, we encounter the Lesser Himalaya zone. This area dates back to the Cambrian to Permian periods, an incredibly long span of time, roughly 540 to 250 million years ago. This zone comprises a significant sequence of sedimentary rocks. We find sandstone, shale, gray wax, that's a type of impure sandstone quartzite, phyllite, dolomite, and even coal beds.
Coal beds, too. Interesting.
Yes, their presence indicates ancient shallow marine or coastal environments, hinting at a time when this land was submerged or lay close to the sea.
Okay, so older rocks, different environment.
Correct. Further north, we delve into the Greater Himalaya. This zone contains even older, late Proterozoic to early Paleozoic metasedimentary rocks.
Yeah, it's sedimentary, so they've been changed.
Exactly. These were once sedimentary rocks, but they've undergone significant metamorphism transformation by intense heat and pressure from the collision, turning them into harder, more crystalline forms like schists and gneisses. This zone also features Cambrian Ordovician orthognous units. These are igneous rocks, originally like granite, that have also been subjected to metamorphic processes, indicating early Paleozoic mountain building activity. Very old stuff.
Ancient mountain roots, essentially.
You could say that. Finally, the northernmost part, high up in the mountains, we find the Tethyan Himalaya. This zone is composed of Proterozoic to Mesozoic marine sediments. These are rocks that were once part of the ancient Tethys ocean floor, the sea that existed between the Indian and Eurasian continents before their collision.
Wow, so seabed rocks now at Himalayan heights.
Precisely. Now they're caught up, folded, and uplifted high into the Himalayan range. Each of these zones contributes uniquely to the complex and dynamic geological tapestry we see in Bhutan today. It's a literal cross-section of Earth's history.
That's a fantastic way to break it down. It truly sounds like each of these periods, each zone, left its own unique geological mark. Can you give us some specific examples of these rock formations? Maybe detailing their lithology, what they're made of, and, crucially, what they tell us about Bhutan's past environments or even their potential for resources.
Let's absolutely delve into a few key formations as they really paint a vivid picture. First, the Shumar Formation. This is a critical metasedimentary sequence. Remember, metasedimentary means originally sediments, now transform.
Right, by heat and pressure.
Correct. Creating minerals like phyllite, quartzite, limestone, and dolomite.
Sure.
You can see excellent exposures of this formation in the Shumar-Karingla area in eastern Bhutan and also in the Kuruchu Valley, where it forms large synforms.
Synforms, like rock folds dipping downwards, like a basin.
Exactly, like a huge geological bowl structure. Interestingly, the Shumar Formation also contains myelinatized granite gneisses.
Okay, that's a mouthful. Break it down.
Right. Granite, common igneous rock. Gneiss is metamorphosed striped granite. And myelinatized. Think of that granite gneiss being caught between two immense grinding tectonic plates along a fold zone. It gets stretched, smeared out, intensely deformed, almost like taffy.
Ah, okay. Sheared and stretched.
Yes, recrystallizing into a new fine-grained rock called a myelinite. These myelinatized granite gneisses are interpreted as tectonic slivers from the footwall. Basically, fragments of underlying rock scraped off and added during the immense thrusting process. While actual sedimentary structures are rare beyond basic bedding, their presence points to a low-energy subtidal depositional environment. Think calm, shallow marine conditions a very long time ago.
And you mentioned mineralization here.
Yes, importantly, this formation is also where some copper and lead-zinc mineralization occurs, showing a direct link between this ancient environment and Bhutan's mineral potential.
Fascinating. What else?
In contrast, we have the Jainti Formation. This one's notable for its vibrant red and gray quartzites. These rocks often show distinct cross-bedding.
Layers at an angle, like ancient dunes or ripples.
Precisely, indicating ancient currents like in a river or tidal flat. And they also show visible mud cracks.
Mud cracks, like you see in dried mud puddles today.
Exactly the same principle. Their presence is a crucial environmental indicator, telling us the sediments were deposited in a supertidal paleo environment, meaning conditions where the sediments were periodically exposed to air and dried out, perhaps in intertidal zones or floodplains.
So a totally different setting from the Shumar. More fluctuating, maybe coastal.
Definitely a different, more energetic and fluctuating setting. Then there's the Manas Formation. This includes limestone, dolomite, slate, quartzite, and gritty quartzite. What's particularly interesting here are the microscopic views of myelinites within its quartzites, clearly illustrated in figures from our sources.
More myelinites, so more intense deformation evidence.
Compelling visual evidence, yes. These tiny stretched mineral grains show the sheer power exerted on the Earth's crust during the Himalayan collision. Moving to the JICA Formation. Historically considered part of the Tethyan Paleozoic succession, it's characterized by gray and greenish-gray garnetiferous mica schist.
Okay, garnet-bearing schist.
With prominent biotite porphyroblasts.
Porphyroblasts, large crystals within the finer rock.
Exactly. Larger individual biotite crystals that have grown within the finer-grained rock matrix, often cutting across the rock's fabric. They tell us about specific conditions during metamorphism. This formation is extensively intruded by basic rocks, which have metamorphosed into amphibolite, and also by tourmaline granite pegmatite veins.
Pegmatites. Didn't you mention those earlier regarding minerals?
Yes, exactly. Some of these pegmatites are notably known to contain valuable beryl, a beryllium-bearing mineral. And there are also quartz veins intruding the Cheka. A fascinating feature here is the gradual decrease in metamorphic grade towards the upper part of the Tethyan sequence.
So less heat and pressure higher up in that sequence.
Correct. The rocks show less intense transformation higher up, indicating varying PT conditions. The basal Cheka formation, for example, has minerals characteristic of the garnet zone, implying very specific metamorphic conditions.
So it's almost like the rocks are a thermometer and a pressure gauge, showing us the conditions they endured.
Exactly. They are the ultimate geological record keepers. Next, the Pangsari Formation. This forms a thick, lenticular body in west-central Bhutan.
Lenticular, like a lens shape, thicker in the middle.
Just like that. It tells us about how it was deposited, or perhaps how tectonic forces later shaped it. It reaches a maximum thickness of about 2,400 meters in the Kanavarti-Dorka track, which is considered its type section.
Type section, the reference spot for that formation.
Precisely. The prime location where that formation is best exposed and defined. Its thickness varies significantly, though, from that maximum down to about 800 meters near Pachu village, and it even pinches out further southeast. Lastly, the Lingxi group, found in the Lingxi Basin. This group is divided into the Mochu, Chibesa, and Amiala formations based on different fossil types: freshwater, mixed freshwater marine, and purely marine fossils.
Ah, fossils, clues to past life and environments.
Definitely. However, this one's a bit of a geological puzzle because some reported fossils, like Marginifera and Favosites, present contradictory ages.
Contradictory, how so?
Well, Marginifera and Spirifernatensis are mainly late Permian, but other fossils reported in the same group could indicate early Carboniferous age, and some others like Dianella and Parahuvites might even suggest Triassic age in basal parts.
So the fossils are giving mixed signals about the age.
Exactly. It suggests a very complex Triassic-Permian sequence and highlights the significant challenges of precise dating and correlation in such tectonically active and deeply folded region. It's like finding pages from different centuries mixed up in the same book, forcing geologists to reevaluate the sequence.
A real geological detective story. Now let's talk about the forces behind all this folding and changing. Here's where it gets really interesting. Understanding the massive, unimaginable forces that sculpted these mountains into what we see today. How do geologists describe the major tectonic structure of Bhutan, which, as you mentioned, is a key active part of the entire Himalayan arc?
Bhutan is fundamentally the poster child for a fold and thrust belt, a direct and truly dramatic result of the ongoing slow-motion collision between the Indian and Eurasian continental plates.
That cosmic sumo match again?
Exactly. Imagine these two enormous rafts of continental crust pushing against each other with immense unfathomable force, bending and breaking the rock between them. This region is divided into four main tectonic zones, each separated by major thrust faults that extend east-west along the entire Himalayan arc. Think of these thrust faults as giant, low-angle fractures, where older rocks are literally shoved or thrust over younger rocks.
Stacking them up like geological pancakes.
That's a good way to put it, like a massive geological deck of cards being shuffled upwards. From south to north, these critical overthrusts are the main frontal thrust, MFT, the main boundary thrust, MBT, and the main central thrust, MCT.
MFT, MBT, MCT.
These aren't just lines on a map. They are immense geological boundaries, literally thousands of kilometers long, representing the primary zones where the crust is shortening and thickening. North of the Greater Himalaya, the Tethyan Himalaya zone is separated by a different type of fault. Normal faults, specifically the South Tibetan Detachment, STD fault.
Normal faults, so pulling apart, not pushing together.
Correct. Unlike the compressional thrust faults, normal faults indicate extension, where blocks of crust pull apart or slide down relative to each other. It's a complex interplay. These thrusts and detachments are massive, dictating the regional geology by stacking and deforming vast quantities of rock, leading to the dramatic, sky-high topography we observe. They are the fundamental architectural elements, the very bones of the Bhutan Himalaya.
When we talk about these massive plate collisions, it's not just about pushing and folding, is it? What kind of fundamental changes are happening to the rocks deep underground? We're talking about intense heat and pressure transforming them on a molecular level, right?
Precisely. This immense geological process involves significant metamorphism, the deep transformation of rocks by heat, pressure, and chemical reactions, all without actually melting them.
Like geological baking, you said.
Exactly. The ingredients, the minerals, are rearranged and recrystallized under extreme conditions. Now, within the lower Greater Himalaya zone, we see something truly unique called an inverted temperature structure.
Inverted temperature. How does that work? Usually it gets hotter deeper down.
Right. That's what's fascinating. Here, counterintuitively, temperatures actually increase from about 330 degrees Celsius to 620 degrees Celsius as you move upwards through this specific zone.
Wow. Why would that happen?
It's thought to be related to the dynamics of the thrust faulting itself, perhaps heat being carried upwards along the fault zones, or shear heating from the friction of the moving rock masses. It's still an area of active research. This inverted structure then continues into the high Himalaya zone, reaching even higher temperatures between 630 and 860 degrees Celsius, hot enough that a key mineral, muscovite, actually disappears due to dehydration melting.
It loses its water and transforms.
Basically, yes, it melts into other minerals. This extreme heat and pressure create distinct mineral zones within the rocks, providing clear indicators of the metamorphic grade, the intensity of the transformation. For example, specific minerals like kyanite appear near the main central thrust, MCT, or in the lower high Himalaya zone, indicating very specific high-pressure, lower-temperature conditions. Further north, sillimanite plus K feldspar, or sometimes cordierite, appear in the middle to upper high Himalaya, signifying even higher metamorphic grades, hotter and more intense conditions.
So the minerals themselves tell the story of the heat and pressure they experienced.
Exactly. We can actually trace this progression in the Boxa and Shuma rocks, found in the lesser Himalaya zone. They start with chlorite-grade metamorphism, that's a lower grade, and gradually transition into schists with biotite, then into garnetiferous mica schist with garnets, and finally into gneiss as you move northward towards the MCT. It provides a continuous, visible record of increasing metamorphism, revealing the deep, hot journey these rocks took.
That's a staggering amount of detail locked in the rocks. So beyond just shaping these incredible mountains, do these powerful tectonic forces also play a crucial role in determining where we find valuable minerals? Is there a geological blueprint that points towards resources?
Absolutely. This brings us to a fundamental question. How do mineral deposits relate to these immense tectonic processes? The answer is profound. Mineral deposits are not randomly distributed.
They follow the geology.
They form in very specific tectonic and geological settings. Think of it like this. Certain recipes for mineral formation require specific ingredients and specific cooking conditions, and tectonic forces provide those conditions. Sometimes a deposit might even form in one place and then be physically transported to another geographic location due to the very tectonic forces we've been discussing, like being carried along a thrust fault.
So they can be moved from where they originally formed.
Precisely. This means that understanding the large-scale regional geology and the specific tectonic processes at play, whether it's intense compression, deep burial, the movement of hot fluids along faults, is absolutely fundamental to understanding and predicting the distribution of mineral deposits in Bhutan. It's like having a deep knowledge of a building's architectural history to understand where its valuable elements might be hidden or where they might have been moved during renovations. Without that tectonic context, you're essentially looking for a needle in a very vast haystack.
That makes perfect sense. And speaking of ongoing processes, are these geological forces still actively shaping Bhutan today, or are we largely looking at ancient history that has now settled? Do we see continuous evolution in the landscape?
Oh, the story is far from over. These geological processes are indeed still actively shaping Bhutan today, continuing to sculpt its landscape in very recent geological timeframes.
Really? Like now?
Geologically speaking, yes. There's clear evidence of continued reactivation of lineaments, those large-scale linear features, often faults in the Quaternary period, which is the last 2.6 million years up to the present. Many of Bhutan's major rivers, for example, the Jaldaka, Amuchu, Wangchu, and Punatsangchu, flow directly along these lineaments.
So the faults are guiding the rivers.
It indicates their ongoing influence on the landscape and drainage patterns. It's as if the ancient faults are still directing the modern water flow. For instance, some valleys are believed to have been abandoned due to faulting in the Quaternary Holocene time. That's just the last 11,700 years. Very recent active landscape changes.
Abandoned valleys.
Wow. We also observe features like triangular faceting on mountain slopes. Imagine mountainsides repeatedly uplifted by faults and then eroded, leaving distinctive, triangular-shaped facets. These are classic signs of active faulting and ongoing uplift. Furthermore, within the younger Siwalik sediments in the south, there are F2 and F3 folds, which are subsequent generations of folds, indicating multiple phases of deformation.
Folding on top of folding.
Exactly. We also see clear evidence of brittle deformation, like shearing along reverse faults in overturned limbs.
Brittle, meaning the rocks fractured and broke.
Yes, rather than just bending, indicating intense stress. And overturned limbs means rock layers folded so severely they're literally flipped upside down. These features collectively indicate that the Earth's crust in Bhutan is still under considerable stress and is actively deforming, constantly reshaping the landscape through faulting, folding, and uplift. It makes it one of the most dynamically evolving landscapes on the planet.
Incredible. So this dynamic geology must have implications for resources. This is where the deep geology meets the practical economy. Based on Bhutan's unique geological settings and what we call metallogeny, the study of how and where mineral deposits form, what specific types of metallic and industrial mineral deposits are geologists predicting or have already identified? What might be hidden beneath this stunning landscape?
Indeed, and the geological insights allow us to predict certain types of deposits with some confidence. Given Bhutan's unique geology, several mineralization types are expected, and some have been partly identified. First, we look for deposits associated with S-type granites. Remember those? Formed from melting sediments in collision zones.
Right, the Himalayan collision granites.
Exactly. This process often leads to hydrothermal mineralization, where hot, mineral-rich fluids circulate, depositing metals like tin, tungsten, and uranium. These frequently occur as skarn-type deposits.
Skarns, where the hot fluids hit carbonate rocks like limestone?
Precisely. The fluids react with the limestone, altering it and concentrating the metals into ore bodies. Next, we anticipate epithermal vein-type deposits, especially in the Tethyan Himalayan region with its leucogranites, those light-colored ones. These deposits are linked to the later stages of post-collisional tectonomagmatic evolution and can lead to antimony gold, SBOU deposits. They form when hot water solutions flow through cracks, depositing minerals in veins as they cool near the surface.
Veins of gold and antimony.
Given that Bhutan's geology is so strongly linked to metamorphism and faulting and collisional processes, orogenic gold is another significant potential.
Orogenic, meaning mountain-building-related gold.
Exactly. This refers to gold veins associated with major fault zones in regionally metamorphosed rocks. Think of gold being squeezed out and concentrated along the major structural weaknesses, like the MCT or MBT created by the plate collision. And related to that, placer gold is also predictable. That's gold weathered out of these primary deposits and concentrated by rivers and streams.
Like panning for gold, but on a geological scale.
Pretty much. We also look for Mississippi Valley-type MVT deposits. These are different. They form after the host rock, epigenetic, typically at low temperatures, hosted in carbonate rocks and dominated by sphalerite, zinc, and galena, lead.
Lead and zinc, like the JICA area you mentioned.
Exactly. The PBZN deposits in the JICA area, hosted in the Shumar Formation, are classic examples. Reported grades range from 3.5% up to an impressive 48.15% lead plus zinc from grab samples.
Wow, nearly 50%.
From grab samples, yes. But overall, it's currently categorized as subeconomic due to various factors like size and extraction challenges. Still, it shows the potential is there. Another important type is sedimentary exhalative, SEDEX type deposits. These form at the same time as their host rock, contemporaneous.
How does that work? Exhalative.
Imagine mineral-rich hot fluids venting or exhaling from the earth onto the ancient seafloor. It mixed with seawater and deposit layers of sulfide ores right within the accumulating sediments.
Like underwater hot springs depositing minerals.
A good analogy.
Yeah.
Then there are pegmatites. Remember those coarse-grained igneous rocks?
Yeah, the ones that concentrate rare elements. And you mentioned beryl in the JICA Formation.
Precisely. They act like natural geological sponges, concentrating elements like tin, tungsten, uranium, thorium, lithium, beryllium, boron, tantalum, niobium, cesium, cerium, zirconium, a whole suite of interesting stuff. The beryl in the Chekhov Formation pegmatites is a prime example. Finally, rare earth elements, REE. These are increasingly critical globally. Potentially useful concentrations can be found in various settings: alkaline rocks, carbonatites, placer deposits, residual deposits from deep weathering, pegmatites, iron oxide, copper gold deposits, and even marine phosphates.
So REs could pop up in multiple geological contexts in Bhutan.
Potentially, yes. And the More Iron Mine provides a specific real-world example of REE occurrence we can look at.
Okay, perfect transition. It's one thing to talk about these theoretical deposit types, but what have actual field observations and detailed analyses revealed? Let's talk about specific sites more first.
Sounds good. Field investigations have indeed provided critical, tangible insights. Let's start with the Moore iron mine in Dagana Donkag. This site reveals iron ores, mainly hematite and magnetite, that are strip-mined from the surface.
From the younger Siwalik Formation, right?
Correct. What's geologically fascinating here is their lamination. They look layered, almost like sandstone. This indicates a sedimentary formation process for the iron ores, not igneous or metamorphic.
So iron-rich sediments laid down.
That's the interpretation. Furthermore, a thrust fault sits right at the ore boundary, highlighting how tectonic forces have likely played a role in concentrating or modifying these deposits later on. Now, within the iron ores, they observed white aggregates of phosphate and carbonate, forming distinct lenticular and thin bands. And the phosphorite zones where these occur show significant P2O5 content, varying from 0.43% up to 23.9%.
And the rare earths.
Yes, even more notably, the total rare earth element, REE, content in these phosphorite zones ranges from 2,677.5 ppm up to 10,289.5 ppm.
Okay, over 10,000 ppm, or about 1%. How does that compare to major global deposits? Is that economically interesting?
That's the key question. Analysis suggests these REEs are likely contained within the iron oxide hydroxide minerals themselves, not just the phosphates. This is indicated by a correlation between REE values and iron oxide amount, and a relatively flat REE pattern without significant anomalies. Now, while the Moore deposit at this grade is lower than world-class REE deposits like Ba and Obo in China.
Okay, so not world-class.
Not yet, based on this data. But its genesis could be a placer or residual deposit formed by weathering concentrating heavy RE-bearing minerals in the hot, humid conditions of southern Bhutan.
Like natural concentration over time.
Exactly. So it highlights a potential resource, even if further work is needed to assess its full economic viability. It's definitely an interesting occurrence.
Okay, what about the graphite?
Kiptishi.
Right, at Kipchishi graphite in Hadzongkag. Here, graphite occurs within graphitic schist, forming bands alongside quartzite and dolomite of the Pero Formation. Geologists identified 3 main bands of this graphite schist, which merge into a single composite band up to 1,500 meters long and over 30 meters wide. That's quite substantial. A big band of graphite schist. What kind of graphite is it?
Most of it is cryptocrystalline, meaning very fine-grained, appearing massive. But a less common flaky variety also exists. XRD analysis confirms it's mainly graphite, quartz, and muscovite. It highlights the potential for industrial minerals in Bhutan's metamorphic belts.
So beyond metals and REEs, Bhutan has significant industrial minerals too.
Absolutely. These are crucial for construction and foundational industries. Dolomite and limestone are abundant, particularly in the southern lowlands where access is better. Deposits in Kataparty and Gongkhola are examples, often found layered with phyllite and quartzite. The Pindon limestone mine is a key active operation supplying the Pindon cement plant.
Essential for domestic construction.
Very much so. Quartzite is another critical resource. High-grade deposits are needed for things like ferrosilicon production for steelmaking. The Pachino quartzite mine supplies Bhutan Ferroalloys Limited and is a prime example. These deposits are found within specific quartzite belts with potential for finding more.
Okay, limestone, dolomite, quartzite. What else?
Gypsum and marble. Gypsum deposits are found in areas like Kathaka, often interbedded with phyllite, and are actively mined with significant proven reserves. Marble, used for construction and ornamental purposes, is mined at sites like Gittafug Top Marble Mine, with other deposits identified near Thimphu and Ha.
Marble for building and decoration.
Yes. And finally, talc. It occurs in lenses, sometimes mixed with quartzite or dolomite, as seen near Pachuseti Kola. It forms through metamorphism or hydrothermal alteration. So these diverse industrial raw materials clearly underscore the economic significance of Bhutan's geology beyond just rare metals, forming the backbone of its domestic industrial growth.
It's a really diverse geological portfolio then. Which brings us to the future. It certainly seems like Bhutan has a rich but still largely underexplored geological landscape. Given all this potential, what are the key missing pieces of the puzzle for future mineral development? Especially if they want to do it responsibly, in line with G&H. Where should the focus be?
You've hit on the crux of the challenge. Despite those initial surveys by groups like the GSI back in the 70s to 90s, systematic, comprehensive geological and mineral exploration across Bhutan has historically been insufficient. To truly promote metal mining development and understand the full scope of potential, nationwide geoscience data is absolutely essential. This includes more detailed geological maps, which have seen some progress, as we discussed.
Right, the mapping has improved.
But a major gap exists in systematic geochemical surveys. That's analyzing the chemistry of soils, rocks, stream sediments to detect subtle mineral anomalies. These haven't been widely implemented.
And airborne surveys, flying planes with sensors.
Those are considered technically very difficult and costly due to Bhutan's extremely rugged terrain and high altitudes. Imagine flying low and slow over those peaks.
Yeah, tricky and expensive.
So the ideal solution often comes down to targeted geochemical surveys on the ground, such as stream sediment sampling. These are highly effective for discovering new mineralized rocks in such challenging landscapes. You sample the sediment in streams, which collects material from upstream, giving you clues about the rocks in the whole catchment area.
A more practical approach for the terrain.
Exactly. Filling these fundamental data gaps, detailed mapping, systematic geochemistry is the crucial first step for any responsible and informed future development. Without better data, any large-scale planning is, well, guesswork.
Makes perfect sense. You can't manage what you don't fully understand. And this brings us squarely back to Bhutan's strong environmental ethos, the gross national happiness philosophy. How does the pursuit of these mineral resources genuinely reconcile with the country's profound commitment to nature conservation, especially in those extensive protected areas covering over half the nation? It sounds like a constant, difficult balancing act.
It is indeed a critical and deeply delicate challenge, and it truly reflects Bhutan's unique approach. Compared to many other countries, Bhutan has notably stricter regulations on conservation, particularly within its 10 national parks and sanctuaries, covering over 51% of its land. Development in the core zones of these protected areas is strictly prohibited, full stop. Even if promising resources were found there, development would have to be abandoned.
A very firm line.
A very firm line. However, the source material discusses the possibility of small-scale geological exploration in multiple use zones or buffer zones within these protected areas. These are areas with slightly less strict regulations.
Okay, so some flexibility on the edges.
Potentially. But even there, any activity would explicitly require a thorough environmental impact assessment (EIA) study to determine and mitigate potential impacts. The report even suggests that, under certain circumstances, exceptional measures might be considered, like simplifying EIA procedures for small-scale exploration that's confirmed not to significantly affect the natural ecosystem.
So very cautious case-by-case assessment.
Extremely cautious. The overarching goal is the coexistence of environmental protection and mining industries, which is deemed acceptable only in very limited areas with proven high mineral resource potential and where the impact can be precisely managed. This calls for extremely careful, nuanced, and deliberate governmental decisions, weighing economic opportunity against profound ecological and cultural values. It's about finding that razor-thin line where progress doesn't come at the expense of happiness or nature.
A huge responsibility. Beyond the geology itself and the policy framework, what about the human element? Does Bhutan currently have the local expertise and the technical capacity to unlock these resources responsibly and sustainably? Or is capacity building needed?
That's a vital question,
Yeah.
because ultimately it's people who drive these initiatives. A significant recommendation from the project report, and a crucial aspect for future development, is the enhancement of human capacity within Bhutan's mining sector. While industrial raw materials like limestone for cement or quartzite for ferrosilicon have seen consistent development and local expertise has grown.
Right, they've been doing that for a while.
Exactly. But metallic mineral resources, apart from iron, have largely not been developed to their full potential.
Yeah.
This is partly because the methods and techniques for metallic mineral exploration and mining differ significantly. They often require more specialized geological, geochemical, and geophysical skills.
Different skill set needed for metals.
A different, often more complex, skill set. Therefore, the Department of Geology and Mines, DGM, needs to actively develop its human resources in this specialized area. The most effective ways to acquire this specialized technical training and facilitate knowledge transfer are through collaborative projects, geological, geochemical, geophysical surveys undertaken with experienced foreign exploration and mining companies or relevant international institutes.
Learning by doing alongside experienced partners.
Precisely. Such partnerships would provide invaluable on-the-job training, expose local professionals to advanced techniques and best practices, and crucially, build the internal capacity needed to manage and oversee new or greenfield mining developments responsibly in the future. It's about empowering Bhutanese professionals to be the stewards of their own geological wealth, ensuring any economic progress aligns with their deep-seated national values.
That capacity building seems absolutely key for making this work long-term. Hashtag tag outro.
Wow, what an incredible deep dive into Bhutan's geological heart. From the ancient immense thrust belts that literally built the Himalayas, creating those dramatic inverted temperature structures deep within the earth.
Truly amazing structures. To the modern-day quest for sustainable mineral development, it's clear that geology isn't just about static rocks. It's about the very dynamic fabric of a nation and its profound values. We've explored how colossal tectonic forces created its dramatic topography and how this complex geological history dictates the distribution of its hidden mineral wealth, from rare earth elements in those unusual iron mines to vital industrial materials like limestone and quartzite.
Indeed. We've seen how historical geological mapping provides the foundational understanding, how active tectonic forces continue to shape the landscape even today.
Still moving beneath their feet.
Absolutely. And how these deep earth processes control where valuable metallic and industrial minerals are found, from those REEs to graphite in ancient metamorphic schists. And it all culminates in a truly unique challenge for Bhutan. How does a country so profoundly committed to its natural environment and the well-being of its people prudently explore and develop its geological wealth, ensuring any extraction aligns with its guiding principle of gross national happiness?
It's not just a technical problem, is it?
No, it's a philosophical one at its core.
So what does this all mean for you, listening in? It's a powerful reminder that even in the most remote corners of the world, every landscape tells a story of immense geological power and profound human choices. Bhutan's journey challenges us to think deeply about how we extract from the earth, not just for immediate profit or resource needs, but in true harmony with nature and deeply held cultural values. It could potentially create a model for a more sustainable interaction with our planet. It makes you wonder, doesn't it?
It really does. And this raises an important question for all of us. In a world increasingly driven by resource demand and the pressures of economic growth, how can deep geological knowledge guide us not just to extract, but to truly coexist with the Earth's treasures, especially in a nation built on the principle of gross national happiness? Can Bhutan, through its deliberate and thoughtful approach, show the world that mining, too, can potentially contribute to the long-term well-being of both people and planet? It's a geological and societal experiment well worth watching.